way to make sure that you're not, now see, you're writing down new probabilities as you go. One way to make sure you don't miss any of those is start with them all written down. Yeah, so 1 1 0, 1 1 1 0, and 1 1 1. Okay, good. Now, what's the average code length of this code? All right. Let's. Hold on.
Oh, you just changed it. Oh my goodness.
Okay, I'm just writing the. Those were the actual symbols that those probabilities represented. Okay. Other way to do it is write them all down. Now I'm just going to connect them together. So same thing he did. 0.25, now 0.2, and that 0.25. Wait a minute. Here, hold on. 1.1 and 0.15 is 0.25, right? So now our lowest is 0.25 and 0.2, which gives us 0.45. Oh, look at this. That, see, you've got.
I didn't know I was supposed to do that.
Yeah, you always take the two lowest.
Oh, okay.
So here's the issue. Yeah, it's not just the lowest remaining thing. You take the two lowest exposed nodes, which may be one of your ones that you've already added up. So 0.45 was bigger than the other exposed nodes, so now we end up with 0.45, 0.55, and we get 1. So let's put 1, 0.
A single binary digit identifying your character.
See, that I did not know.
Yeah,
So when we
that's.
get 0.25, could we choose the other 0.25?
Yeah, I could have arbitrarily chosen the other 0.25, and that would also be another. It would be another Huffman code, and I'll show you in just a second. So let's see what we get here now is I get. Oh wait, let me do it with zeros so that I do it the same way you did it.
Sam, yeah.
You did 0 on the top. 0, 1, 0, 1, 0, 1. So I get 0, 0 for A, 0, 1 for B, 1, 0 for C, 1, 1, 0, and 1, 1, 1. So let's see if that actually made any difference. If we do the average code length for your code, we get 0.3 plus.
Yeah, it's a doctor.
That makes sense.
2 times 0.25. See, now that we'll call that the Pecora algorithm. It's and this will be 0.2 times 3 plus 0.15. Okay, so 2.4. Thank you. And then if we do the Huffman code, we get 0.6 plus 0.5 gives us 1.1 plus 0.4 gives us 1.5 plus 0.45 so 2.25. Okay. So it does make a little bit of a difference, right?
Weak sauce.
All right. Now, you pointed out this, at some point here, we could have done this slightly differently. Let's,
back at the 0.45.
right, at the 0.45, we could have taken, hold on.
Just rewrite it. You'll be all right.
Yeah, let's just do the whole thing. Okay,
Oh, dude.
so too small, dang it, wrote on my leg. 0.25. Now, we could have taken, instead of those two, we could have done these two and done 0.45, right?
No, but it has 0.25 and 0.3.
Now our lowest ones are 0.25 and 0.3. 0.55 and then 1. Now the only problem with that is now we have a crossover. Does it matter? No, it shouldn't matter at all. But now let's look at what our code is going to be this time. We're going to do 0, 1, 0, 1, 0, 1, 0, 1. So now A is going to be 1, 0. No, yeah. A is going to be 1, 0. B is going to be 0, 0. C will be 0, 1. D is 1, 1, 0. And E is 1, 1, 1. So the average code length will be exactly the same. It's just we changed slightly some of the equal probability values up top. It just switched around our 0, 0, 1, 0, and 0, 1. Make sense?
Yeah, it was.
Just trying to prove a point.
You need to find a point because apparently I'm not smart enough to get it.
And humble you a little bit.
And humble me, yeah.
Oh.
I don't want to go by the first one. That's not my thing.
All right. So now the other question is this an optimal code? Does it satisfy Shannon's theorem? So next thing we need to do is let's compute H for this. So H equals minus 0.3 log 0.3 plus 0.25 log 0.25 plus 0.2 log 0.2 0.15 log 0.15 plus 0.1 log 0.1. Anybody have an answer for that one?
Is it log or log?
Well, it's log, yeah. These are all log based too, but
LG.
well, you could just do whatever log and then divide the whole thing by log 2, right? So you could use natural log or log base 10,
Right.
whatever.
So
Just divide the whole thing at the end by log base 2.
And it did like 2.25 for some reason.
It should be slightly lower than 2.25, but it better be bigger than 1.25.
2.23.
Wow, all right. So we got pretty close here then. Let's, yeah, a quick hint on your calculator. An easy way to do this is H equals minus 1 over log whatever. Let's say we're using log 10 of 2 times 0.3 log 10, 0.3 plus all the rest of that stuff, right?
Well, yeah, for ours, when I put my log in, you have to put the base in.
You put the base in.
It never,
okay.
It doesn't assume that you have to put it in.
On the, okay, so yeah, you guys have a little nicer calculators than they did last time where they used all those yellow. Oh, okay. Yeah, if your calculator does not have a log base 2 built into it,
We run a function.
then, okay, write a function, or you can type it into Wolfram Alpha or whatever.
Right.
I didn't claim that I wrote that first.
Okay. Everybody more or less happy with Huffman coding? Well, there'll be a homework assignment for you. Play with
It
it.
doesn't really matter if you get it in your
All right.
Okay.
Okay, so we will talk about one thing here. There's information about we can figure out all this rate and h prime, which is h per second, and s prime is how many bits per second we get. So h prime has got to be less than s prime. Question is, so the information rate is h prime. So the question is, can the channel carry that? Well, number one, we have bandwidth constraints. We can't just use infinite bandwidth. So if h prime is really high, then no, we can't do that. And channels add noise and distort the transmission, so we've got lower rate because of that. So the question is, what is the channel capacity? What's the most information we can send through it? I didn't mean to offend you that bad, man. I'm sorry. It's like, head with it. All right.
You're calculating.
Okay, so we can do all this conditional entropy stuff, which is called equivocation. This is the average surprise you will have if you were to find out what the source really transmitted after you see the output. Right? If the channel is perfect and we see the output, then we'll have zero surprise if we see the input, because it should be the same. Anyway, so because we saw the output, our surprise about the input is reduced. Amount by which it's reduced is I. Anyway, we're not going to get through all this, but main thing here, maximum mutual information is the channel capacity, which is C. And it is given by let's see, here we go. We're just going to kind of go through the rest of that because, frankly, I hate to see I'm worried about whiplash on some people here. Whoa. Main point here, entropy is going to be 1/2 log 2 of 2 pi e, that should be e to the sigma squared, where sigma is the standard deviation.
E, or is that something else?
That's e, the base of the natural log.
Okay.
Yeah. That's e to the sigma squared. And the channel capacity, this is the main one you need to remember, is channel capacity C equals B, which is the bandwidth, times log 2 of 1 plus SNR. In this case, you notice we're taking log 2 of it, so this SNR is probably not going to be already a log. So this is not in dB. This is just the signal divided by the noise. It's the actual just flat ratio of signal to noise. And you'll see this a lot, channel capacity theorem. Okay, so it's got it on the slide that's not in dB. All right, moving on to error control coding really quickly. Did you guys talk about Hamming coding in math?
I think it's in the book.
Okay.
I'm just saying it. I think it's in there.
All right, so general idea is Hamming code is the number of, or Hamming distance between two code words is the number of bits where the codes differ. So if I have 110 and 111, what's the Hamming distance?
2.
One bit, right? Because there's only one bit where they're different. How about 1101 and 0001?
All different.
No, the last two were the same, I think.
1101
versus 0001. Yeah, okay, right.
I'm not trying to be difficult, I really.
No, you're right. I know. As I was saying it. Okay, so 1101, 0001. What's the Hamming distance? 2, because these two bits.
Really, it's just the number that are different in the whole string.
Yep. That's all the Hamming distance is. Okay, so that's between two code words. of the entire code is the minimum pairwise distance. So I hope you'll be able to reproduce this diagram. No. It's a four-dimensional hypercube. If somebody wants to bring in some marshmallows and toothpicks and try and make a model of this, that would be cool too. There we go. Especially if you can do it in 4 dimensions, then you definitely get extra credit. Well, anytime. I mean, mathematically, you can extend all this stuff to any number of dimensions. You know, you have in spatial dimensions, there's x, y, and z directions, right? So if we add x, y, z, and then say now we've got a w and a t dimension. Now we've got 5 dimensions,
Could you
but
theoretically break down any additional dimensions in reference to x, y, and z?
no, they're a completely orthogonal, independent, extra direction. It's this is where math starts getting really, really screwy.
Talk about communication, not warp theory.
Wait, what did you think we guys were getting? We're getting to exactly. It's, yeah. All right. So yeah, general idea is. Well, and in this case, most of the time when we talk about 4D, we're talking about 3 physical dimensions plus time. In this case, not so much. These are just 4 independent mathematical dimensions. You notice that the Hamming distance between any 2 points on this is 1, right? So I can go from anywhere to anywhere by only changing 1 bit. And it makes a 4-dimensional cube. So a 3D cube with connected to, well, anyway, yeah, it's not real easy to visualize. Okay, so we have a couple of possibilities. If D equals 2, then we can do a 1 error detecting code, which is just a parity bit. Parity bit can detect 1 error, but it can't tell where it is. If D equals 3, we can do 1 error correcting code or a dual error detecting. D equals 4, we can do a single error correcting or a dual error detecting or a 3 error detecting. Anyway, and so forth. So the more the distance, the more we can do. Hamming code is a single error correcting, dual error detecting code. It can detect up to 2 errors, and if there's only 1 error, it can fix it. Make sense? Okay, so these have to be independent errors. They can't be bursty errors. What are bursty errors?
A bunch.
Yeah, like when you have a whole block of screwed up bits. It's not a particularly good one. There's not a table. A lot of error correcting codes have a table lookup, so you can just put them in a ROM on your source device, and that has a similar ROM on the receiving device. But it's an algorithm. Here's the general idea. Any code, now this is a 16-bit Hamming code, right? Here, let me get my little pen out on here. So up here, this shows us the bit position. We just number them from 0 to 16. You'll notice below that, each one of these is just the number that's above it in binary. So for example, 5 here is 0101, which is just 5 in binary. Do you need a minute?
Yes. Does anyone who rides a motorcycle? Anyone bring it in? Anybody have a BMW motorcycle?
Is your lights on?
Is it the only BMW motorcycle out there?
I didn't ride today.
Okay, because probably not because I have a key. So.
I think there's one in the 53 cord.
So,
Okay, I'll
Wade, are you trying to find out who you hit this morning? Is that what's
side?
Yeah. This is the one laying on its side under your car out there? Is it?
There's a body under it.
There's a body there.
Geico commercial. Oh my God, is there red
Mayhem.
Mayhem. I am mayhem.
Thank you, sir.
I didn't ride today.
Appreciate it.
Can't figure out how Wade got the key to that. Anyway.
They left it in the block.
Oh, in the body. Okay. All right, so Hamming code, this is the easiest way to do it. It's just write down each bit position in binary, right? 5 here is 0, 1, 0, 1. And then, right, so here, let's use bit position 7. How do we write 7 in binary? 0, 1, 1, 1 is 7, right? Okay, so all these numbers here are just the bit position written in binary. Now, here's the actual message. The message is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. That's it. Why are they written just on these weird little spots here and there? Okay, right. These are the M's are the message and the P bits are the parity. What do you notice about where are those P bits? Tell me what their bit positions have in common.
They're all like powers of 2.
Yeah. Okay, every power of 2 is a parity bit. So bit position 0, 1, 2, 4, 8. The next one would be at bit position 16, and the next one would be at 32 if we went that long. Okay, so now here's the way that it works. Each one of those parity bits it's parity for just the message bits that have a 1 in that power of 2. I realize that doesn't seem to make a lot of sense. But for example, let's see. Parity bit 1 right here, right? It has a 1 in that last position. So what we're going to do is take the parity of every other bit that has a 1 in that position. So we're going to take 0 and 1. So far we have 1, 1, 2 1s. We have 2 1s, so the parity is even, and we'll put a 0. If we had an odd number of 1s, we would have to put a 1, right? Okay, same thing for 2. 2 has a 1 in this row, so everything else that has a 1 in that row. This one, this one, this one, this one, this one, this one, this one. So here we've got 0. There's a 1. There's 2 1s. There's 3 1s. So that has a 1. So far, so good? Major Yarmer was like, what the crap?
So you're going down the columns for the row you just circled.
Right.
Oh, yeah,
This is Hamming code is it's a little bit complicated to do, but it actually makes a little more sense
You
later.
put a 1 because it was even or odd?
Well, no, it's even. There's 4.
We're doing even pair. Wait, are there 4?
No. There's only
There was.
there's only 2, I think, right?
You're counting how many ones.
Wait, yeah, I'm counting how many 1s. So there's no 1s.
But it's
There's
got a cross
1 1.
2-bit.
There's 2 1s. There's 3 1s.
Where are you? I'm sorry, I'm
Yeah,
lost.
yeah,
Where you
yeah.
looking?
Okay.
Change color and.
Yeah, let me change color and do it differently. Okay, so we want to take a parity of everything that has a 1 in its power of 2 line, right?
Is that selfish told? You say it like
Okay, let me circle this. So bit 1 is going to have every odd numbered bit, which are the ones here that I'm circling in red. Although that turned black for some reason. I don't know. I must have hit the button here.
Those have a 1 in the first set.
Okay, all of those are the odd numbered bits, right? So 1, 2, there's 2 of them. So since there's an even number of 1s, we put a 0 in bit position 1. Now, number 2 is going to be every place that there's a 1 in this row. So that means we're going to use this one. I'll just do it in blue on top of it. These 2. We'll skip 2. These 2. Whoops, I got off by 1 there. Sorry.
It corrects them. Oh, no.
These, there we go, those 2 and those 2. So I count up the ones in there. 1, 2, 3, so this becomes 1, right? Okay, now
It's an odd number of ones.
it was an odd number of 1s, so now there's an even. If I just extend this like this, right, now this is one of the parity bit itself is in there. Total, there's an even number of 1s now. 1, 2, 3, 4, including the parity bit, which is what you want. Let's do the 4-bit one.
So you just made that whole power even. Okay.
Right. Now, the 4-bit,
What's
everything.
the example exactly? That's what I'm trying to understand. Is what the example that you have is the code that you're trying to write?
Yeah, this is
Okay.
what we're trying to write is what we're going to send. So now we're going to do the ones that have a 1 in the power of 4. So it'll be, I'll draw a little thing below here. These 4, then we're going to skip 4, and it's going to be these, whoops, these 4. Okay, so we're going to have 1, 2, 3, 4. So yeah, that one's going to be 0.
Okay, is there a reason we didn't do the zeros?
Didn't save for last.
Yeah,
Oh.
0 parity we're saving for last.
Right.
Then 8 is just going to be these last ones. So it's going to be 1, 1, 2, 3. So that needs to be a 1. Then, as you said, we do the 0 parity at the very end, which is every one of the other bits. We count them 1, 2, 3, 4, 5, 6, 7. So that's going to be a 1. So what we actually send is 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0.
Wow.
It should be even.
And right, this should have an even number of 1s. 1, 2, 3, 4, 5, 6, 7, 8, which it does.
And this is the Hamming code.
That's the Hamming code.
Single error correction, double error detection.
Right. So let's look at what happens. Let's see what happens if we get an error. Let's say that we send that. Zero, one, one. Zero, one, zero, one.
That's what I was at. The example that was up there, all the M's, that is your original
One,
message.
zero. All those M's, yeah,
So you
those.
were trying to figure out what the parodies would be with that original message. That's what
Right.
That's why I was sitting here lost. I was like, where the hell is he getting this from?
Oh, okay. Sorry, those were the original parody. Those the message were the ones that were printed there. The parody ones were the ones we wrote in. So we ended up with this, and this is what got sent. So that was going on over at the sender. Now at the receiver, we receive this. We know that we're using a 16-bit Hamming code. So what we're going to do is say, first check. Well, just for the heck of it, let me.
Can you throw the green one up to me?
Okay. Oh,
Just
thanks.
so you know, you can take it.
Nice.
Oh.
Look at that on camera?
What's this from? He's like spinning on his head.
Our expectations just went up.
Dang it. I should have dropped.
Bad throw, bad throw.
Okay, so
Yeah.
at destination, what?
All right, so at the destination we receive this. First check we do would be,
0.
yeah, parity bit 0. We check to see if there's an error. So let's count them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Would you count the 0 bit though?
Yeah, you count every bit.
Well, they're
Okay.
uneven numbers. So
There's an uneven number. So what that tells us is P0 equals 1. That means we got an error. Actually, what this tells us is there are an odd number of errors, right? There's either 1, 3, or 5 errors, but there's nothing. We're saying that this is fairly short. We're assuming errors are independent and relatively far from each other. So we're assuming that that there's only one error in here. So now the question is, where's the error?
And then you can check the other parity.
Okay, so now we check the other parity bits. So parity bit. Well, let's start at the. Okay, so we're going to do. Let me write this down at the bottom. P8, P4, P2, and P1, P0. P0 was already 1. That just tells us whether or not we've got an error, right? So now let's find P8. It's going to be 0, 1, 2, 3, 4, 5, 6, 7. It's going to be these last 8, right? And so we just count them. 1, 2, 3, 4, 5. Oops. P8 has to be a 1 to make that even. Okay, so first off, we already know that our error is someplace in that part, right? So now next step is we do 0, 1, 2, 3, 4 to there. The way I think of this, I don't know if it helps, is P8 is you skip 8 and then take the next 8. With 4, you skip 4, take the next 4, skip 4, take the next 4. Right? And that's exactly what, if you look up here, in this one it's skip 8 and then it's the next 8. But it's just whether you want to write down all those numbers or just do this skip version is up to you. So P4 is 1, 2, 3, 4. So that's a 0 because it's already good. Next step is P2. So we skip 2. We can count 2. We skip 2, count 2, skip 2, count 2, skip 2, and count 2. So 1, 2, 3, 4, 5. So that one's got a problem, right? Then P1, we just do every other odd one. So this one, there's 0, 0, 1, 2, 3, 3, right? So P1 equals 1. Now, what does this tell us?
What's wrong?
What's that? Yeah, this tells us exactly where the error is. It's in bit 8 plus 2 is 10, 11. It's in position 11, right? So now I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is an error. Is that true?
Yes.
Yeah.
Yep, that's the one I changed. So it tells me exactly where the error is. And what should it be? Well, it could only be the opposite of whatever it is. So we just flip it, and now we fixed it. We don't have to retransmit. We're fixed and good and gone.
So 0 bit just simply tells you if there is an error.
Right.
And then you can
Technically, it tells us whether there's an odd number of errors, but yeah.
So if there's multiple errors, you're screwed?
Well, not necessarily. Let's make it so there's 2 errors. Okay, so here, that one, and let me put this one in green so that, and that one's an error. Okay.
Okay.
So now let's go back through this. Now P0, let's count them all. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 ones, so P0 is 0. Now we could just say, all right, no errors, and move on. But all we know is there's an even number of errors, which is 0 if there are any. Now, so we need to check the rest of these. If they all come out 0, then we can assume there were no errors. It may not be exactly true, but it probably. We're assuming that it's only going to be 1 or 2 errors for this. So let's check it out. 8, we've got 1, 2, 3, 4, 5. Oops. Okay, now as soon as we've done that, we're done. As soon as one of those came out non-zero, we know there are multiple errors, and we're just going to have to resend. There's nothing else we can do.
So there's more than one
Well,
error.
I thought it was double error detection, so that just means it can
That means
detect if
there.
there's more than 2.
No, it can detect 2. If there are 3 or
That's what I'm
more,
saying.
they
When
could.
you go through this, it doesn't. It just knows there's more than 2. There's 2 or more.
It just knows
errors,
there's
not
2
where.
or more. It has no way of determining where.
Oh, okay, so I was thinking something. All right, got it. I knew
So
it was
I mean,
correct one.
yeah, we could do the rest of these, and like this next one, we've got 1, 2, 3, so that's a 1. Here we've got 1, 2, 3, 4, 5, so that's a 1. We've got 1, 2, 2, so that's a 0. But this number now doesn't tell us anything. If P0 was 0, then the other numbers being 1 just tells us that there are 2 or more. Only if there's 1 can we determine where it is. Now what if there were 3? We'd get a 1 down there, whoops, and then we would get something, and we would actually have a wrong answer, right? If there were 3 errors, it would say there's an error, and it would give us a bit position. We would fix it, and we'd still be wrong.
And how does it know that then?
It doesn't. That's part of the problem with you. You can really only use these things in places where the probability of that many errors is extremely low, right?
Yeah.
Okay. So in general, we use higher level. We use like a whatever. But out of 16 bits, the probability of 3 or more errors on a relatively decent channel should be pretty low. Okay. So anyway, that's how you do that. Location of message bits are where the M's are. Location of partial parity bits are where those P's are. And then PK is just the XOR of all those message bits if BK of J equals 1, which is what we just did, right? This is just the math way of saying it. So here's the example that we just did, written in so that you can see it and look at it later. And then here's the partial parities.
That was 16.
Well, yeah, okay, this is wait. Oh, yeah, it is a 16-bit. Sorry, I don't know how 14 got in there. My bad.
Can I dumb this down just to make sure?
Yeah.
Can we go back?
Sure. To here, or?
Am I understanding correctly that like your code word where you made the error where you got 8 is equal to 1?
Uh-huh.
What you're doing is you're adding a parity bit to make sure that 8 is equal to 0 when you do this.
Right.
And we know there's an error when you do the second half of 8. You know that somewhere in there that something else happened to make it.
Exactly.
Okay.
And then, see, the nice thing is, if you look at the way these overlap, you can see that it'll narrow it down to one single position, depending on which of those parity bits have
I
an
think I was
error.
tripping myself up because I was getting fixated on what the 8 was changed to and trying to relate it
Oh.
there, but that's not right.
No.
It's a completely separate event.
Yeah, this stuff was all happening at the receiver. We just received some code word, and we want to know if it has errors. Because of the way that we've done this, we don't need to know what it was or how we constructed that. We just need to know that it's Hamming encoded, and we take the appropriate bits out and do it.
Was this built off of somebody else's work, or was this sort of like an original thought that somebody...
This was an original thought-ish. I mean, I'm sure it was built off. I'm sure he looked at other people's stuff, but but this is more or less an original thing. Now, this is actually a really, really simple error correcting code. The reason we do it in here is because, hey, we can do it by hand, right? More complex ones get a lot more complicated. So here's this is just an example. So here, again, P0 equals 0, and then we got different partial parities, so the number of errors is not 0 because we got a 1 someplace, which means we've got more than one error, which means we can't correct it.
So for the one where you're saying where D was higher and it increased the amount of error detection, and, I can't remember the it also increased the amount of error correction.
Right, we can.
And when you increase the D, what is that, like how many bits you're actually using?
That's how many extra bits we have to add to it. Yeah, and there's different methods. Hamming code is just single error correcting, dual error detecting. Then we have lattice codes and a bunch of other things to do higher level ones. But yeah, the more errors you can detect, the more overhead you have to add. So
that one, there's already 5 bits that are parity, so you only have 11 of the 16 for that.
right. So even with this, we've added quite a lot of overhead, right? We've added, what's 16 divided by 11? About 50%, not quite, but
16 divided by 11?
yeah.
Doesn't over?
Yeah, but doesn't it use
Doesn't this all have to
You mean 11 divided by
have to do with
16?
encryption?
No. 16 divided by 11 is 1.45, so 45% extra, right? The 1, if it was 1, that would be adding nothing.
This all relates to encryption.
So this is just error correcting stuff. Now, once you start talking about encryption, now you've got additional overhead even beyond this stuff. So that's why, like, Zipper is a lot lower bandwidth than Nipper is, because it's got extra encryption added onto everything, right? And then when you do higher level encryptions, I mean, the more overhead you have for every level of encryption. Now, well, not always. Encryption can sometimes happen without a whole lot of extra overhead. Like, for example, a Caesar cipher. How many of you are familiar with that? It's pretty much the same thing. A Caesar cipher is you write one letter on each piece of lettuce, you make a Caesar salad. No.
Toss the salad.
Didn't just write everything backwards or something like that?
Well, not exactly. What it does is yeah, you use a letter as a code letter, and then you have an offset from everything shifts a certain amount in the alphabet based on that. It's not just the simple, like a rote 3 cipher would be, A would be A, B, C, D, A would be D, B would be E, and so forth. Those are the easiest ciphers, is just shift stuff over by a letter.
No, really, like no one can read.
Yeah, no. Yeah, that was pretty secure. Caesar cipher is not even much more trouble than that to break. These are all relatively simple ciphers. And then you get up to like PGP, which is almost impossible to break. But, you know, we're talking about 128-bit lengths for the cipher keys, and we'll get into that later. But yeah, all of these things add overhead. Error correction adds overhead. Ciphering, encryption adds overhead. We're not going to spend any more time on hamming. I realize that just doing the one example isn't a whole lot, but luckily you have one in your homework to play with. Yeah, I knew. What's that? Yeah, and then that's what I was going to say. It's break time, and then when we come back, we'll start on the next slides.